Into chapter 6 we go with the shapes of molecules and intermolecular forces. So on our previous exploration of this, we spoke about those covalent bonds, the sharing of electrons between two atoms. Now what is important not to forget is that though the attraction to those electrons is what is holding the bond together, holding the two positive nuclei close by, those electrons are still repulsive to other electrons, and though two electrons themselves can live in an orbital, what we find is that they are repellent towards the electrons in other orbitals because of their electrostatic charge. Now, if we think in 3 dimensions, if there's nothing to prohibit, what's going to happen is the electrons are going to push away from each other. The pairs are going to push away from other pairs and get as far away from each other as they physically can. Now, this is going to determine the shape of the molecule. It means that, for example, some things, if I had like 4 bonds and I basically had them coming out like spokes of a wheel, that's not the most that they could get away from each other, because what we could do is we could pull 2 out of that plane into 3 dimensions, and suddenly they've managed to get slightly further apart. The bond angle between them has increased slightly, and that is indeed what does happen. For something like methane, which has 4 bonds, it separates those 4 bonds as widely as it can. In fact, the bond angle for this tetrahedral shape is 109.5 degrees. Simply, in 3 dimensions, 4 things can't get further apart from each other. Now, drawing this is quite difficult. We have the advantage here of these lovely 3-dimensional diagrams, but for many, many years, chemists have been stuck drawing structural formula like that one there of the methane, bottom left. Now, to demonstrate the 3-dimensionality of this, they invented a kind of code. They codified the 3-dimensional shape. And hydrogens basically coming out of the page towards you were represented at the end of a thick black wedge. And those disappearing behind the paper were denoted by like a dotty wedge. And so you could almost imagine the 3-dimensional shape. We must also consider the effect of whether or not that pair of electrons is involved in bonding or not. You see, it could be a bonded pair, electrons held in a covalent bond between 2 nuclei, or electrons could exist as a lone pair, where they're not involved in bonding at all. They're just outer shell electrons sitting together in an orbital. Now, what is the difference between these two? Well, the bonded pair is feeling an attractive force to a nucleus on the other side. It actually pulls them slightly further away from the nucleus than they otherwise would exist. It means that they're not as proximal to the point in the center. The lone pair have nothing pulling on them, and so they actually nestle and snug further in. If you imagine like a bicycle wheel, and you imagine the spokes leading from it, what happens is the lone pair is closer to the axle and the bonded pair slightly further out. Now that means that if we have situations where we have bonded pairs and lone pairs, those lone pairs that are closer in naturally are going to be closer to other electrons. They're closer to the center of the atom. They're closer to the center of that bike wheel. It means that being closer, the electrostatic force from them is going to be greater because of their proximity, because they're just not far enough away from the nucleus to give themselves space, basically. Whereas the bonded pair, they are going to separate from each other a lot more. The force between them is going to be less because they're further from that center. Now, this means that the forces of repulsion are greatest from lone pairs, less so between lone pairs and bonded pairs, and then the smallest between bonded pairs and bonded pairs, all because of the proximity to each other as a consequence of how close they are to the nucleus of the atom. And so this explains the shape of ammonia. Now, ammonia has 1 lone pair and 3 bonded pairs. The lone pair is close to the nucleus and has a greater than average repulsion. Just because it's closer, it pushes the 3 bonded pair away, and it forms this trigonal pyramidal shape. like it's a triangular bottomed pyramid, not a tetrahedron. In a tetrahedron, all of the sides are exactly the same. This one has got the bottom triangle is of a different size to the three side triangles, so it's pyramidal instead. Water has two lone pairs. If you look at this incorrect diagram on the top right, you can see that that's not right. That's not stable. Those electrons will move until the lone pairs are on the same side, pushing everything as far apart as they can do. And that's ultimately what's determining the shape of these molecules. It's only stable, it only exists and will persist in that shape when it has got to its most stable configuration, when everything has pushed away from everything as much as it can do. And so for water, the most stable configuration is to have the two lone pairs on the same side. It actually twists and contorts the water molecule into this boomerang shape. Now we could draw this in 3D with one hydrogen coming at you and one hydrogen going behind, but this is totally not necessary. If the molecule is confined to a two-dimensional plane, as in this water molecule, it's perfectly acceptable to draw it in 2 dimensions. Carbon dioxide has this double covalent bond, and it has no remaining lone pairs. It means it's perfectly symmetric. You could draw a line right down the middle of it. It means that the molecule that carbon dioxide forms is linear, with a bond angle of 180 degrees. Now, sulfur dioxide is a chemical very much of the same nature as water, in that it has got a lone pair on the sulfur in the center, and then it's got these double bonds to the 2 oxygens on either side. Now, that lone pair pushes the 2 double bonds away, just in the same way that the single bonds to the hydrogens in water were pushed away. In fact, the angles would even be the same. If you remember boron trifluoride, it only had 3 bonds because the boron itself has only got 3 electrons that could be involved in bonding. Now, if they are all involved in bonding, it means it forms this 3-bonded molecule. Now, a really good question that could be asked here is, why does this molecule sit in a flat plane? Well, it's actually to do with the nature of 3-dimensional space. That you can actually write an interesting little proof, if you like, that the furthest 3 objects can get away from each other in a 3-dimensional volume is on a 2-dimensional sheet. It is basically, they have 120 degrees between them, and it makes no sense to have to involve 3 dimensions. They will sit on a flat plane in the same way that a water and a sulfur dioxide molecule will. So this shape, like a fidget spinner, is a trigonal planar shape. Now, our rule-breaking sulfur hexafluoride, remember how it was using those D-shell orbitals to randomly invent rules for itself and have additional bonds in that outer shell? Well, it doesn't really look like this image here, this idea that it sits like a flat wheel. Of course, they are going to repel away from each other and they're going to push each other out of that alignment. So they're not going to sit on a flat plane, because if I've got 6, they're going to push each other into basically a shape of 4 with 1 above and then 1 below. Now this forms an octahedral, and this is sometimes a bit challenging for people because people say, well, it's only got 6 corners. How can it form an octahedral? Well, though an octahedron has 8 faces and 8 sides, it still only has 6 corners separated by 90 degrees. You can see that little diagram there. So with things that have 6 identical bonds, it forms an octahedral shape with a bond angle of 90 degrees. Whether or not you have a single or a double bond, it doesn't matter. Whether or not you're an ion or an atom, it doesn't matter. Whether or not you've got dative covalent bonding or regular covalent bonding, it does not matter. These basic shapes and these bond angles are going to be the same. For example, methane and ammonium, CH4+, are going to have exactly the same tetrahedral shape. Though the atoms might be bigger or smaller because they're actually bigger or smaller atoms, the actual shape and the bond angle of 109.5 is the same. SO42- with two of those double bonds again has this tetrahedral shape of a bond angle of 109.5. And here, the carbonate and the nitrate ions, they are trigonal planar just because they have three bonds, a bond angle of 120 degrees.